Hello, I'm Shane Brinkman-Davis-Delamore, and this is Code and Optimism, a show where we explore how to solve problems faster with software. Today we continue our exploration of good modular design. We have previously dived into the first three of the 5 essential elements: purpose, interface, and encapsulation. And today we are going to continue with connection. We just have 2 more left: connection and implementation. I'm excited to get to them. PIE, Purpose Interface Encapsulation, or PI, is kind of the nugget of the module. That's kind of the, all right, we're going to build a module. It's got to have an interface. It needs to be encapsulated. It needs to have a purpose. And then connection and implementation seem a little bit removed. And that's because they're starting to move towards the bigger, either the outer picture or the inner picture. It's kind of inner space or outer space. So let's take a look at connection today, and then we'll look at implementation next time. And we will have gone through the 5. So continuing on this theme of elements, the element for connection is wood, which is to say trees. And that is because the connection graph of modules is a tree. And the connection graph, I mean dependencies, the dependency graph. And so the shape of the dependency graph is a tree. So I think that ties nicely to wood as the element. So why does connection matter in modular design? Well, the key thing is that modules don't exist in isolation. They are used together in a network. There is a connection graph, a relationship between all these modules. And those connections between modules also adds complexity to our system. In order to succeed in minimizing our complexity of the whole system, we need to minimize the complexity within a module, and we need to minimize the complexity between modules. This is really the key insight here with connection, is that even though we could potentially, in an extreme sense, we could take our complicated app and we can make any number of really simple modules, like a file or 2 each, 100 to 200 lines of code. Each module will be really simple and clear, but our application, which maybe it was 100,000 lines of code or 500,000 lines of code, will now be 5,000 modules. It'll have 5,000 module size graph. We have not won anything there. We have still lost out. So as you're considering modular design, you have to realize that you have to both minimize the network, the size of the network your module is going to be used within, as well as minimizing the complexity within your module. So let's talk a bit about the modular connection graph. The reason why it's a tree, most importantly, is that strong encapsulation says that each module should have its implementation be completely encapsulated and hidden from the rest of the world. So whatever a module itself depends upon should be invisible to the rest of the world. So if we consider this, what we're looking at right now, to be like a module, this is all you should be able to see, is the collapsed version, just the external interface. All of its internal dependencies, you should never be able to see. And that right there creates a tree-like structure. And from what I'm going to call the strong module point of view, all of coding is actually within a modular hierarchy. Everything we do, because even when you're just writing a single expression, 1 + 2 × 5, that plus is itself a module that you're using. And then you might have some multiple statements or expressions together. That becomes a bigger module within maybe a function. If you recall, a few episodes back, we actually went into what the grand view of the whole modular structure, hierarchical structure. And the insides of our modules are themselves a modular network, and the place where our modules are used are also a modular network. So yeah, well, I just said here, every module participates in the connection graph through its interface, and every module conceals a connection graph in its implementation. So think of it as a tree. In reality, it's probably a directed acyclic graph. And for those of you who want a quick refresher, that's basically like a tree, but where some children can have multiple parents. As long as no child is itself its own ancestor, which is to say if you follow the parent graph up, it doesn't eventually get back to the child again. So that's to say there's no cycles, acyclic. Then it's a directed acyclic graph. And this is actually perfectly okay for good modular design. Totally fine for it to be a DAG because, for example, I just mentioned the plus operator is a module. Well, probably other modules also depend on the plus operator. That's okay. The point is that it's encapsulated and hidden. Like, you don't really need to know that other modules depend upon that. It's irrelevant that multiple other modules depend upon it. Even though if you drew it as a graph, you would have a directed acyclic graph, not a strict tree. Which is why I still think it's most useful to think about it as a tree and to visualize it as a tree. Much like here with my mind mapping software, you can see I made the primary link off of this parent node of, in reality, it's a, and then the subnode is directed acyclic graph, but I made the secondary link a different color pointing at the other node. And that's a good way to think about it and a good way to sort of manage the complexity mentally if you have a DAG sort of relationship, you want to sort of think of it as a tree. So let's dive into the do's and don'ts. We're going to do don'ts first. So connection graph don'ts. First one we kind of already said a little bit. Never have circular dependencies. Just don't do it. By definition, you think about it, circular dependencies are going to make complexity. You can have one, if you have a module depending on another module, which in turn depends back on you, literally you've almost created an infinite loop of dependency there. And I'm looking at you, Node.js and NPM. The most common complexity with managing modules is when you have these circular dependencies. And Node and NPM, I'm sure people who have used them have seen many times, oh, you've got a peer dependency. You have to manually install the peer dependency. Oh, warning, you've got a peer dependency inconsistency. So many errors around peer dependencies. And Node itself allows you to circularly, one file can import another file, which can then import the original file again. And in my opinion, that was a big mistake. You don't need to have it. There's always a way to solve it without having circular dependencies. And they just create a lot of headache. You should never, number two, should never depend on the internals of another module. This is just the strong encapsulation principle again. The internals of another module are private to that module. If you break encapsulation, you've broken the complexity fighting superpowers of that module. So you can only use another module through its interface. You never reach into another module for dependencies. And as I've said before on previous episodes related to this, I think you should consider directories as modules. And so pathing into a directory, requiring a folder and then requiring into a subfolder that is breaking encapsulation. That is reaching into another module. And last, and this one's a little more subtle, avoid implicit dependencies. Now, what do I mean by implicit dependencies? An implicit dependency is when a module A imports, say, an email module that sends emails. And then module A imports that email module, doesn't do anything with it really. It just immediately passes it on to another module B, and module B is the one that actually sends the emails. Module A imported this dependency, then it passed it through to another module, and so even though module B does not explicitly say it depends on that email module, it does, obviously does, because it's the one using it. Module A was just a pass-through. It was a detour. So implicit dependencies imply a failure of encapsulation. The module B in this scenario is the one that is dependent on this emailer, but that dependency is now leaked out into module A. Module A now knows about this dependency and is interfacing with it, which has added not only two dependencies where there could have only been one, but it's also added an implicit dependency. And so by definition, it's not explicit, so it's not clear. Like, other programmers will not understand that actually it's B that's using the emailer, not A, and A is an irrelevant sideshow that just is involved in the chain. So I call this no detours. Don't have a detour. Minimize the number of steps along the dependency graph for data or functions or classes or whatever you're getting out of another module. Minimize the number of steps for it to get from where it is to where it's going. And I'm looking at you, React.js anti-patterns. I've seen this with fairly common in tutorials around React.js where some state will be imported into a parent component, that parent component will do nothing with that state at all, but immediately pass it to a child component. And so that child component is actually one that depends on that state. The parent component does not actually in practice, but it now has this implicit dependency because it's being passed through. And the reason why this is done, I presume, is to make that child component stateless. It is just a pure functional component, and you want to be able to test it in a pure functional way, and you want that parent component to be the one that interfaces with the state. I can see that being a good argument, but the modular complexity is being ignored. And in fact, I actually think the modular complexity supersedes there. It is actually a worse solution to have a pass-through dependency than to have to deal with testing component B with some state rather than being able to test it without state. So no detours. Make sure your dependencies are as direct as possible. Some connection graph do's. And this is actually the really pretty simple one. Minimize your dependencies. That's really the big thing. You should, across your entire app, minimize your dependencies. And remember, files are dependencies, directories are files are modules, directories are modules. If you import a file, if you import a directory, that is a dependency. So the simple version when you're looking at your code is just go and draw a picture. I think it's really useful on any project of any size. Draw a picture of your dependency graph. And there are probably tools out there that can help you get there, but you should actually be able to take every single file in your code, look at the import statements, literally make a node for every file in the graph, and then draw a line from every file to every file it imports. And then look at that graph. How complex is it? How many dependencies do you have? I would probably just ignore your imported dependencies initially. So the stuff that you're pulling in from a public package manager, look at that separately. That's important too. But you also want to look just internally, how you're designing your own modular dependencies. So draw a picture. And here's the key thing with drawing a picture. You should be able to hand that picture to a new programmer on your project who's never looked at any line of code in your project. Maybe they have the highest understanding of what you're trying to accomplish. And they should be able to look at the name of the files, the name of the modules in your dependency graph, look at the arrows in the dependency graph, and say, I totally get it. Totally obvious why that depends on that. It's totally obvious why the to-do list component depends on the to-do state. I mean, obviously it's going to. That isn't a logical dependency. If you've got a lot of dependencies, which are like the login screen depends on the to-do list, then you're going to be like, why does the login screen depend on the to-do list? Does that really make sense? And then you might realize, oh, well, your login screen is actually, maybe it's actually effectively the router. Like the login screen lets you log in, but then once you're logged in, then it switches you to rendering the to-do screen. And it's not really dependent on the to-do screen. It's actually passing that to-do state down to a to-do rendering component, a subcomponent. That's where you're going to start to see, oh, we're making this way too complicated. It should really be the to-do list component that depends on the to-do state. And the login screen should probably actually be its own module separate. It shouldn't be a super module, etc. So, the takeaways. At the top level, the connection graph is a tree, or a bunch of trees, a forest. And each module has underneath it submodules that it's using, and they've got relationships to each other. Each module is used within a parent context where there's a graph. And you want to, for success, balance the complexity of the modules with the complexity of their connection graph. Minimize explicit dependencies, minimize implicit dependencies, and never create cyclical dependencies. And really that's it. It's easy to say, difficult to master. Once again, we're at the end of another episode, and thank you so much for spending your valuable time with me. I really do believe time is the most valuable thing all of us have on this planet, and the fact that you've spent some of it with me means a lot to me. So thanks, and remember, all problems are solvable with enough knowledge.